Syed Hassaan.
Okay, can you see my screen?
Yes. Yes.
Okay,
No. No.
perfect.
We see now.
Okay. All right. Good morning, everyone. Thank you very much for joining in today's meeting. In this class, I will be focusing more on the gas lift systems as economical means of artificial lift. Gas lift systems have been around for quite some time. They were invented back in early 20s and 30s, 1920s and 30s as one of the measures to use to pump oil to the surface. Um, and over the period of time, over the decades, they have actually evolved to be one of the most economical means of artificial lifting a oil and gas well. So the agenda is that we will start with some history on the gas lift systems. Then we will talk about unloading sequences, different type of gas lift equipment, the gas lift valve mechanics, and then a little bit on the application engineering. Right. So as I mentioned earlier, gas lift has been around for quite some time. And it's very important to understand what gas lift is because not a lot of people actually know about it and how it works. It is used very frequently around the globe, uh, but the mechanics behind them are very simple. Um, but uh, Familiarity by the people to this technology is a little bit less compared to rest of the different artificial lift systems. So gas lift systems essentially uses a very high pressure gas to supplement the formation gas. And what happens is that the high pressure gas is actually injected in between the space between the tubing and the casing. So what you see over here in the green is the tubing, and what you see over here in the white is the casing. And this high pressure gas is actually injected at a very high pressure into that space. And what actually happens is that this gas travels through annulus, this space that is between this tubing and the casing. This is called annulus. It travels through that, and then it enters through a gas lift mandrel, through a gas lift valve, and then it mixes with the formation fluid, the fluid that is coming from different formations into the tubing. When it mixes with that fluid, it reduces the fluid density in the wellbore. And what happens is that when it reduces that density, it lightens the hydrostatic column. And when it lightens the hydrostatic column, it reduces the back pressure on the formation, and formation can actually push more fluid into that tubing. When it pushes more fluid into that tubing, consider this as a cyclical cycle. It will push more fluid, and that fluid eventually will reach the surface and into your flow line. So it's a very simple mechanism in which we can actually use. It doesn't have a lot of rotating components. It's very simple to install. It's very economical. And primarily, we use this method to unload the gas well and produce the oil and gas all the way to the surface. So here are some of the components of the gas lift systems. The most important component of the gas lift system is something which is called gas lift valve and a side pocket mandrel or a gas lift mandrel. Uh, these gas lift mandrels are actually installed as part of the completion of the well. They are permanent installations, which you can see over here, right over here. Side pocket mandrel and the gas lift valve. It's inside the pocket of the side pocket mandrel. Usually, a well will have multiple side pocket mandrels and gas lift valves. In this well, you can see there are three side pocket mandrels. Uh, on the surface, you have your gas separator, your stock tank, your flow control valve, and your gas compressor. So one of the important things, as I said, we need very high pressure gas to be injected into that annulus, which is the space between the tubing and the casing. So that high pressure gas usually is compressed by a surface gas compressor. The gas is usually is the one that is coming outside from the well. We use the same produced gas to we pass it through a separator, and then once it's a clean gas, it's not wet gas, then we can use a gas compressor to compress it, inject it into the annulus, and then produce more fluid. So in this way, the gas is actually part of, it is recycled continuously. Now, as I mentioned earlier, that one of the most important components of a gas lift system is a gas lift mandrel and a gas lift valve. This is just a zoomed in view of a gas lift mandrel. You can see this is like a centric tubular component. And then there is a small pocket which is cut inside the gas lift mandrel. And in this pocket, there is a gas lift valve. Now, gas lift valve is made up of two main uh, components. The one is called a latch, and the second one is called a valve body. Now, the latch is essentially there to lock this valve in place so it doesn't move. And the valve is there, it has some mechanisms, different type of valves will be required for different type of applications. And this gas lift valve essentially will provide that necessary pressure for the injected gas to mix with the formation fluid and lightens up that fluid column. A little bit of gas lift history. The gas lift was invented back in 30s and 40s, came into the production, more widespread um, usage in 50s and 60s. It was invented by a company called Camco. Camco was the first one who invented the gas lift mandrels, valves, and the wireline equipment that is required to change the valves. In 1999, Camco was bought over by Schlumberger, which is called SLB now, and it is still part of SLB. Over the period of time, the technology has proliferated, and different competitors have come up with their different versions of the gas lift mandrels and the valves, but essentially the working principle still remains the same. Now, why gas lift systems are considered economical means of artificial lift oil and gas production is because of several reasons. The first one is the lower operating cost. You can see that it doesn't have a lot of rotating components. There are not a lot of moving components. It's just two main systems, your valve and the mandrel, and then you have surface compressor. So this helps to reduce your replacement and maintenance cost, and then you have a very less upfront capital expenditure. It's a surface-driven system. It uses compressed gas, which is often readily available on site, minimizing fuel costs. So you don't need to have electricity on site. You don't need to have generators on site. All you need is a produced gas, and then you can use that gas to run your compressor as well as use that gas to be injected as injection gas. The second part is flexibility and scalability. It is very flexible method of artificial lifting. It has a very wide operating range. So it can handle a very wide range of production range and fluid composition, especially when there is a lot of gas, very less fluid. That means your gas to oil ratio is very less. It is very flexible in that conditions. And then it is very easily adjustable as well. You can adjust your injection rates, your depths can be modified, you can pull your gas lift mandrels, you can install them deeper, you can install them shallower. And then you can also do multiple changes by changing your gas lift valves only without changing your mandrels, which can be done through a wireline system. So you can change your injection rates without actually pulling your tubing as well, which actually saves you on the intervention costs. The longevity is also one of the key benefits of using a gas lift systems, since there are not a lot of moving components and most of the moving components are already on the surface. So it's not subjected to very harsh downhole conditions. It doesn't um, get a lot of interaction with the H2S on the surface. So you can have a higher longevity, very high reliability, and very easier to service as well. Longer equipment life, since most of the components are already on the system, on the surface, which you can easily access, they tend to last longer and are easier to service as well. Then utilization of the produced gas. Since gas that is used as an injection gas is actually a byproduct of production, which would otherwise be either flared or re-injected back into the reservoir, then we are using this produced gas as an injection gas, which adds a lot of value and reduces waste. And then higher production capability as well. Since the injected gas can be injected at a very high pressure, So you can actually have a very high production capability as well, which makes it ideal for a well with like offshore wells where there is a very high production, as well as onshore wells which have depleted over the period of time and the production is much less. It is applicable on all of those production scenarios. So very versatile production method, very reliable, not a lot of maintenance that is required, and not a lot of very high upfront capital expenditure, which makes it ideal as an economical means of artificial lift. Now, how the gas lift well actually works. What happens is that initially, you can see over here, let me explain this. You have a wellhead, surface wellhead at the very top. Uh, this is your tubing, this is your casing. These are your gas lift stations with the mandrel of the valves installed inside them. What actually happens is that you have to be very careful when you are unloading the well. That means unloading the well means that the well is dead, it's not producing. Now you have to push it to produce. So you are gradually starting your gas lift system. So you have to be very careful. Usually you keep your pressure between 550 to 100 psi per 10 minutes. That is how gradually you increase your pressure. And you try to unload between 1 to 2 barrels per minute. That means that is your flow rate that you try to hit. You don't try to get too aggressive at the very start. You try to do it very gradually. So you start injecting your gas. What happens is that you gradually increase your gas injection rate. You are monitoring your well cleanup and stability, and then you get to the target position. So this is your target position. What actually happens is that the gas lift valves are all open, but once it reaches to the target depth, this valve will open and it will inject the gas into the tubing. And then once it enters the tubing, it mixes with the fluid, lightens the fluid column density, reduces your back pressure on the formation, and then it produces all the way to the surface into your flow line. Unloading valves, these are usually required during the unloading phase, only open when the annulus and tubing pressure are high enough to overcome your valve set pressure. So these are your unloading valves. That means they are normally closed. But once you actually reach a pre-assigned or pre-designated pressure, they will open and they will let the gas pass through the annulus into the tubing. And now, as soon as the pressure drop, it will close again because then your pressure will go to the next station. They can be activated. They actually open at the pre-designated pressure, so they can be spring actuated or nitrogen charged. There are two types of gas lifts flows. One is continuous flow and the other one is intermittent flow. What continuous flow is that it is applicable for the wells which are producing naturally as well as the wells which are not producing naturally. It can be used to kick off a well that will flow later naturally. It is used for the backflow injectors, for lift aquifer wells, as well as unloading of the fluids in the gas well. That means, for example, your gas well or your oil and gas well is already shut down, it has been killed, you want to restart it, you do it through a gas lift. So this is how continuous flow works. As the name suggests, the injection gas is injected continuously and the well produces continuously as well. So you are producing your gas, or you are injecting your gas over here, and then it goes into the tubing and outside into the produced fluid. So this is how your constant gas flow well dynamics or trend will look like. You have your depth on the y-axis and you have pressure on the x-axis. What actually happens is this is your fluid uh, uh, flowing tubing pressure gradient. This is your pressure gradient of your tubing, and this is your casing pressure. What actually happens is that the tubing pressure and the casing pressure, as you start going deeper, that starts increasing. There is a point where actually your casing pressure will overcome uh, or it will actually reach the same pressure as your tubing. This is where when you start seeing the gas lifting. And this is usually the operating pressure of the gas lift valve as well. So after that, what actually happens is that the pressure of your since the pressure after this point of the tubing will start increasing, so you will start lifting your well and you will start unloading all the fluid as well. For the continuous flow operations, there are different type of configurations where in which continuous flow operations works. One is called a single zone gas lift installation. That means you have gas lift manual right over here. There is a production packer right over here. Um, you are injecting through the flow control valve into the annulus, and then you are producing through this gas lift manual. Then there is what we call a dual string gas lift installation. That means you have two tubings inside the well. This is tubing number one. This is tubing number two. What actually is happening is that it is actually producing from two reservoirs. You can see over here, you have your dual string packer, which is only open to this reservoir, and then there is another single string packer right over here. What is actually happening and why you are doing this is because you don't want to mix the two reservoirs or two formations together. You want to produce them separately. The reason for that could be because one of the production formation could be producing a lot of water. You don't want that water to go inside uh, the other formation. The other one could be that one production formation has a very high pressure. There is a high pressure differential between the two formations, between formation one and formation two. So you don't want high pressure formation to damage the low pressure formation. So you actually isolate them by using the packers in between. And then you use two tubes, essentially two tubings, to produce your uh, fluid. Then there is something which is called chemical injection gas lift installation. You have your traditional side pocket mandrels with gas lift valves in as a part of this tubing. And then at the very bottom, there is a special type of mandrel, which is called a chemical injection mandrel with a chemical injection valve. Why do you want this? Because sometimes there is a lot of scaling uh, in the well. You want to reduce it by injecting chemicals to prevent that scaling. So you install a chemical injection mandrel and a chemical injection CIV, chemical injection valve, as a part of that gas lift installation. So you can accomplish not only gas lifting, but also the chemical injection as well. And then which is something which is very, very uncommon is called macaroni installation, which is very much similar to the dual string installation. The only thing is that rather than having a traditional side pocket mandrel, you have a conventional mandrel. That means you cannot pull out these valves as part of your intervention campaign. It will always remain a permanent structure down the hole unless or until you pull your tubing. Then there is the other form of gas lift operation, which is called an intermittent gas lift operation. As the name suggests, this is not continuous. It's a non-continuous operation. That means you will inject the gas, you will wait for the fluid to come to the surface. Once the fluid is produced, you will wait again, you will inject, and until a certain pressure is met, you will wait until then, and then it will inject, it will produce again. So you can see over here, the fluid is right over here. The level is really low. All of the valves are closed. You can see the valve 1 all the way to valve 5 is all closed, and the fluid is right over here. In the stage 2, what actually happens is that the very bottom valve will open. You will inject gas. Your pressure is still low, but you are injecting gas, injecting gas, injecting gas until your fluid column start moving up and up and up. Then what happens is that it will reach all the way to the surface. When it will reach all the way to the surface, your pressure will on the gauge will start. It will show the flow line pressure, and once the flow is completed, then it will go back to zero. So your fluid level will again go down. Now you will wait and you will let the gas eject and you will wait for the pressure to build up until that column of fluid is transported all the way to the surface. Gas lift, let's talk a little bit more about the gas lift mandrel and gas lift valves because these are the key components of the system. The gas lift mandrel is usually part of your tubular and it is made up of CRA materials. What are CRA materials? These are corrosion resistant alloys or your carbon steels. Um, you have your mandrel, which is the one shown in the picture is called what we call a side pocket mandrel. Why it's called side pocket mandrel? Because you have a pocket right over here on the side, and then you have a through bore access right over here. So if you have to do any logging or any production intervention work, your tools can actually pass through gas lift mandrels without actually damaging your gas lift valve because it is out of the way. The valve is actually held in place by a latch, which is right over here, and then this is your valve body right over here. Side pocket mandrels primarily come in two sizes. They have a 1 inch pocket right over here or 1.5 inch pocket. The reason why somebody would pick up a 1 inch pocket or 1.5 inch pocket is based on your production and your pressures. So usually low pressure reservoirs, low production onshore reservoirs will use a 1 inch pocket. And as you go deeper, you need more injection pressure, then you will use a 1.5 inch pocket. They actually come in a round shape and an oval shape. That means if you do a cross section, you will see either a round shape or an oval shape, and they are compatible with the tubing. The material selection depends primarily on your produced fluid properties as well as your uh, uh, pressures. That means if you have a very high reservoir pressure, then you need to select metallurgy which is more suitable for it. Usually we start with the 4130, 4140, and it goes to all the way internal 718, 925, which are nickel-based alloys. Key components of the side pocket mandrels are your orienting sleeve, which is right at the top. I will talk about it at the end of my slide, what the orienting sleeve is for. Then you have your forge pocket right over here and tool discriminator. The tool discriminator is essentially just a machine channel or a force test channel, and that is there to prevent any other tools from going inside which you don't want to be inside or interact with your side pocket mandrel. So it acts like a guard. Orienting sleeve. Orienting sleeve is primarily a component that is part of the gas lift mandrel, and it plays a very important role when we are changing the valves. The orienting sleeve actually helps in guiding a tool. If you can see, it has a guiding profile. It helps to guide a tool that can be used to change, pull, or push a gas lift valve. As I mentioned earlier, gas lift systems are usually very flexible systems. You have the flexibility of changing the valve over here through a wire line intervention or a slick line intervention without actually pulling your tubing. So when you have that flexibility, you need a special tool to change that valve, and that special tool requires some sort of orienting profile to go inside this pocket and change the valve because it's entirely mechanical tool. So for that, you actually have what we call a orienting sleeve. Now, gas lift equipment, as I mentioned earlier, is very versatile. It is used not only for onshore production operations, but also for offshore production operations. Offshore, you have a different type of mandrel, same operating principles, better metallurgy, better dimensions, and better design as well. Because it is more optimized for offshore operations, that means it is usually more expensive as well. On these offshore mandrels, you will have these special channels that are cut inside the valve body, very specialized. And these channels are cut so that you can actually pass your cables, your injection tubes, tubing, things like that. Um, because it's a very big component, so you need some sort of protection. And gas lift mandrels through these machine channels actually provide that protection to your bypass cables. One of the important components of the gas lift system is what we call a latch. Now we are going to talk a little bit more about the latch because the latch is there for a very important purpose. It locks the valve in place. That is the main purpose of this latch, as the name suggests. This latch also helps in some other things as well. It makes sure that it protects the valve which is below it. This latch is actually screwed onto the valve. This ensures that the valve is protected, that the debris don't go inside the pocket. And it also has this the G-type profile, which actually helps to lock it in place. And with the pressure fluctuation, it makes sure that the valve will not fly out of the pocket when you are injecting the gas. There are different type of latches. There are solid latches. There are latches with the holes drilled inside them. That totally depends upon your application. We are not going to go deep into how the latch selection actually works. But what you need to understand is that it is there for two main purposes: to lock the valve in the place in the pocket and to protect it from all the scale, debris, and tools that are passing through the gas lift manual. Now, gas lift valves have different types as well. These are there. These types have evolved over the period of time, over decades, to accomplish certain purposes, but the main principle still remains the same. There are three types of gas lift valves. There are dummy valves. These are just nothing except solid piece of metal inside the pocket. And then you have unloading valves, you have orifice valves. Your unloading valves are essentially either your casing pressure operated valve or production pressure operated valve, IPO or PPO valves, and then your throttling valve. And then your orifice valves are always open valves. That means they are not dependent on the fluid pressure. They will always remain open, but they have a small orifice in it. So actually they act like a choke valve. That means it is there to achieve certain pressure. And then you have some specialized valves as well, like your circulating valves, your water flood valves, and your chemical injection valves. Chemical injection valves, as I mentioned earlier, is there to inject chemical using a gas lift mandrel and a chemical injection valve to inject chemical into the reservoir. Now, gas lift mechanism. So gas lift valve mechanism actually essentially is very simple. As I mentioned earlier, these are either spring operated or nitrogen charged, that if a nitrogen charged valve, and they are preset so that your valve will open at a certain pressure only. This is a very simple. This is your gas lift valve right over here, and I have done a comparison with a pressure regulator. So it actually is just a pressure regulator, and it is operating and working in a very similar fashion. So you have this is what we call a stem tip. This is called a stem. This is your spring, and this is your diaphragm, uh, or bellow as well. Uh, what actually happens is that your casing pressure will come over here and it will act on this surface, essentially on this piston surface right over here. And it will keep on acting and acting until it reaches a point where it will overcome the spring force. So your pressure will overcome your spring force. The whole assembly will move up, including the stem tip. It will move up. When it will move up, the gas can inject through this port into your gas lift mandrel and into the formation fluid. So this is how the gas lift valve is essentially work. It's working on a pressure differential scenario. So these are some of the equations that we actually use in setting up a gas lift valve. There are three type of pressures that you need to uh, keep into mind. You have your PB, which is your pressure bellow. You have your PC1, which is your casing pressure. And then you have PT, which is your tubing pressure. What happens is that FO, the force that is required to open the valve, is essentially, if you remember, your pressure is force divided by area. So if you use that formula PC to calculate that force of opening, what you do is you multiply your casing pressure with your differential area. So area of bellow minus uh, this AP plus tubing pressure. So PT, which is the pressure of the tubing that is acting upon on the small surface area right over here. And when you have to calculate the force of closing the valve, what you have to do is PC2. That means your casing pressure multiply your with your bellow area. That would be the force that is required to close it. As I mentioned earlier, these are just some of the type of valves. W valves, which you can see right over here, is just a solid piece of metal. Then there is something which is called equalizing dummy as well. We are not going to go more into detail of it, but essentially it is one of the types of W valves. Then the most famous are the injection pressure operated valves. Injection pressure operated valves, as the name suggests, depend on your injecting pressure that you are injecting from the surface. So these, if you can see over here, these have spring as well as nitrogen charged dome. So what will happen is that you will set this dome pressure to a certain pressure. That would be the pressure that would require to overcome it when you are injecting it from the surface. Orifice valves are typically, they are always open valve. That means they will always allow gas to go across whenever there is a positive pressure differential. The gas injection is controlled by the size and differential across the replaceable choke. So these gas lift orifice valves actually have a small choke in it. It's just like either it's a square edge orifice or either it is a venturi type uh, profile. And what it actually happens, what it actually does is to make sure that you are getting the pressure you want. You are always injecting at the pressure you want, because that is crucial in getting your fluid all the way to the surface. And then at the very bottom, if you can see right over here, there is something which we call a back check. This back check is essentially to make sure that the valve, there is no backflow communication. This is just a zoomed in view of the different type of valves. You can see it right over here. These are always open valve. You can see the back check profile right over here. The back check is essentially this yellow component. And then this blue thing is your square edged orifice. And then you have a venturi type orifice as well, which you can see right over here with a venturi type profile. Nova or the venturi type profiles, they are meant for more efficient um, uh, gas injection. They were a step above the square edged orifice, usually are considered a premium product. Uh, they are just there for more um, to make sure that more gas passage is available and there is a minimum differential across the orifice. Uh, this is what you can see right over here. What actually happens is that this is a traditional orifice valve, and this is uh, a Nova or a Venturi type orifice valve. What actually happens is that with the Nova, you can actually have injection pressure, which is very close to uh, essentially your tubing pressure is very close to your injection pressure. That means you will have a more efficient production. Then valve material also depend upon your formation fluid, your pressures, and your temperatures as well. Usually it starts with stainless steel 316, and then it will go to all the way to the nickel alloys and all that good stuff. Then you have these packings as well. If you have to remain standard, then you use a nitrile and neoprene packing. But as you start going more high pressure, then you have to look for more premium packing. Monitoring, control, and optimization, what to monitor. There are many parameters that you have to monitor to make sure you are optimizing and injecting your gas at a most optimal rate. Surface parameters that you usually monitor are your gas injection pressures and rates. The tubing head pressure and the temperature will be measured at the wellhead and then produce oil, water, gas. That means you want to understand how much oil, water, and gas you are producing. and then
Professor,
certainly
once
your two
we have
questions.
only 10 minutes, just try to sum up,
Sure,
conclude your presentation
sure.
because we have time to manage the questions and suggestions in 10 minutes. Sorry.
Almost done. It's last few slides only. And then you have your downhole monitoring. I'm going to talk about downhole monitoring in the next slide. But essentially, you want that monitoring to make sure that whatever you predicted during your installation in terms of your formation pressures, your injection pressures, your produce pressures, you are still getting the same one. Downhole monitoring in a gas lift valve, a gas lift well is usually accomplished by multiple. You have your permanent downhole pressure and temperature gauges, which are part of your completion. Then you have also something which is called CTS gauge, which is cable to surface gauge. That means it is part of it. If you can see right over here in this blue, yeah, this gauge is installed as a part of your tubing, and there is a fiber optic cable or a cable that runs all the way from this gauge all the way to the wellhead. There is a component on the wellhead which is called a cable penetrator, which helps to seal around the cable, and then it will go to your SCADA stations. You can use different type of other sensors as well. One of that sensor is called DTS sensor, or distributed temperature sensor. This is essentially a fiber optic cable that runs all the way through the length of the well. And what it does is that it will actually trend the temperature profile of the well. So what will happen is that wherever you will have the gas injection, you will have a lower temperature because of the Venturi principle. You are injecting gas, so you are injecting gas at a very high pressure, you will have a temperature drop. You will have a temperature drop, your DTS sensor will pick up that temperature drop and it will trend that temperature drop, and you will know that you are having an efficient and active gas injection. This is a little bit expensive. Usually I've seen it being installed offshore, but sometimes it can be installed onshore as well. And then
Hassan,
your slick line and E-line surveys. Your slick line and E-line surveys are there to ensure that you can do the logging to measure your production and all that. With that, I can conclude my presentation. Thank you very much for listening to me patiently. We are open for questions.